Hello everyone. Today we are going to discuss a couple of number sense problems. The first one, prove that n to the power 9 minus n cubed is divisible by 504 for any integer n. For this type of problems, we first do the prime factorization for 504. It is actually equals 7 times 8 times 9. We know 7, 8, and 9 are relatively prime with one another. So we only need to prove that n to the power 9 minus n cubed is divisible by 7, by 8, and by 9. We start with h. First, we factor out n cubed from the expression. We have n cubed times n to the power 6 minus 1. N to the power 6 minus 1 can be further factored as n cubed minus 1 times n cubed plus 1. Then I rearrange the terms. We have n cubed minus 1 times n cubed plus 1. This is a product of three consecutive integers. So why the product of three consecutive integers is a multiple of 8? We will do a casework. The first case, if n is an even number, then the middle term, n cubed, is a multiple of 8. 2 times 2 times 2. The second case, if n is an odd number, then the first term and the last term, n cubed minus 1 and n cubed plus 1, are two consecutive even numbers. For two consecutive even numbers, one of them must be a multiple of 4. Then their product is a multiple of 8. So by these two cases, we conclude that the n to the power 9 minus n cubed is divisible by 8. Now we look at the case for 9. Again, we factor out n cubed. Further factorization, we got 3 cubic polynomials. Then the casework. This time, we have 3 cases based on the module of 3. If n is congruent to 0, that means n is a multiple of 3. Then n cubed is a multiple of 9. Actually, n cubed is a multiple of 27. Case 2, if n is congruent to 1 with module 3, then n minus 1 is a multiple of 3. Also, n squared plus n plus 1 is also a multiple of 3. You can plug in the residual 1. 1 squared plus 1 is 3, which is a multiple of 3. So therefore, n cubed minus 1, by factoring, we have n minus 1 is a multiple of 3 times n squared plus n plus 1, also a multiple of 3. The total would be a multiple of 9. Similarly, if n is congruent to 2, then both n plus 1 and n squared minus n plus 1 are multiple of 3. Therefore, n cubed plus 1 is a multiple of 9. So the case for 9 is done. Finally, we look at the case for 7. This is the easiest case. In fact, we can factor out n squared instead of n cubed. From the expression, we have n squared times n to the power 7 minus n. The second term, n to the power 7 minus n, is a multiple of 7. This is a direct application of Fermat-Little theorem. If you're not familiar with Fermat-Little theorem, I give you an alternative proof. Again, we factor out n cubed from the expression. For the factorization, and the second, the last cubic polynomials can be further factored. We have n cubed times a linear term, a quadratic term, another linear term, another quadratic term. The next step is crucial. It is congruent to another expression with module 7. So what I did here is, I carried n cubed and the linear term n minus 1, another linear term n plus 1. For the two quadratic terms, I replaced their constant term 1 with negative 6. 1 with negative 6. You see, the difference is 7. So the two expressions are congruent with module 7. Why do I want to do this? Because the new quadratic polynomials are easy to factor. It is actually the first quadratic polynomial is factored as n minus 2 times n plus 3. The second one is factored as n plus 2 times n minus 3. And we rearrange the terms. We have n minus 3 times n minus 2, n minus 1, n plus 1, n plus 2, n plus 3. So it contains a product of 7 consecutive integers. One of them must be a multiple of 7. The job is done. I have a couple of exercises. The first one, n to the power 5 minus n is divisible by 30. So you can use the approach we just discussed directly to this problem, an easy case. For the second one, n squared times n to the power 100 minus 1 is divisible by 2020. The proof is also similar. If you study the problem carefully, you will see there's a lot of other factors of this polynomial, like 3, 11, and something else. In other words, n squared times n to the power 100 minus 1 is divisible by a number that is way larger than 2020. However, I created this problem as a dedication for the year of 2020. This is a very special year. Everybody has a lot of memories, and good or bad. By the end of the year, all of us deserve a celebration. Happy New Year.